So our project was heat transfer in practice. We compared the forced convection of hot coffee against the natural convection of hot coffee. My name is Brendan Ekstrom, along with my group mates Joel Galtieri, Mike Kurtz, Nick Appling, and James D'Agostino. So I'm going to get into it right here. Just a little overview of what we were looking at. So as we all know, drinking is a very big staple of American culture. Around 62% of the country today drinks coffee. We realize that it's very common for people to get hurt from drinking coffee that's way too hot. So we decided to prevent injury in the future. We made an experiment which we performed to determine the best effective way to let your coffee cool before taking a dangerous sip. The experiment determines the best method by comparing the heat transfer rate of a cup left to cool in ambient stagnant air to that of a cup which is a forced air current blowing over the top at a constant velocity.
In order to perform our experiment, we needed to create a natural and forced convection environment. To make a natural convection environment, we just used a still room with an ambient air temperature of 17 degrees. To create a forced convection environment, we used a fan to create a steady flow of air across our cup of coffee. We heated water to 83 degrees Celsius and placed it in a cup and measured it as it cooled. We did this in still air environment and with the fan on and measured temperature as it cooled at 30 seconds, 1 minute, 1.5 minutes, and 2 minutes.
The first mode of heat transfer we used in our consideration for the experiment was forced convection. Forced convection is classified by the mode of heat transfer, and in this case it'd be the bulk motion flow from an external force. In our experiment we would use a box fan to create this external motion. During forced convection there would be two boundary layers that are formed on top of the surface, a thermal and hydrodynamic or velocity boundary layer off the hot coffee. For the first model on the left, the box fan would be blowing over a cup of coffee in this case instead of the rows of circuits out of the model from the textbook. And on the image on the right is two boundary layer distributions for forced convection. The velocity distribution layer occurs first over the hot surface, which would be the coffee, and the temperature distribution would be occurring over the top of the coffee cup. For our calculations for forced convection, we first found the properties of water, which we assumed to be similar to coffee, out of the back of the textbook at the T-film temperature of 50.25 degrees Celsius. From there, we calculated the velocity of the box fan from the manufacturing table on the back of the fan. From there, we calculated the Reynolds number. After the Reynolds number, we found the Nusselt number and used that to find the heat transfer coefficient in watts per Kelvin. We then used the heat transfer coefficient to use the Newton's law of cooling to develop how many watts total were transferred during the process. And from there, we found the convection rate using the mass transfer of density of water in the cup. And from there, we calculated the time for the experiment for forced convection.
For natural convection, we took a very similar approach we did for forced convection. We found all the properties of water, which were the same because we used the same temperatures. We found the film temperature to be 50.25 and beta to be 0.02. Instead of finding the Reynolds number, we found the Grashoff's number, and we used that and the Prandtl number to solve for Nusselt. Once we had the Nusselt number, we found H to be 19.62. After we found H, we used that to find our total heat transfer rate, which was 38.9 watts per second. And then after that, we found our mass to be 0.36 kilograms. And we used that, our heat capacity, and the temperature difference at our measured times to get our heat transfer at the times we measured for. Once we had those values, we divided the total heat transfer by our rate to find our times to be 49.87 seconds and 69.15 seconds.
Experimental study resulted in a faster cooling rate for forced convection compared to natural convection. This is shown in our graph where natural convection displayed a temperature drop of about 32 degrees Celsius over 240 seconds, where forced convection results in a temperature drop of 38 degrees over the same time span. This is because natural convection has a cooling rate based alone on natural effects such as buoyancy force. This means that coffee in stagnant air has no external source to aid in heat transfer and occurs naturally. Forced convection, in our case, uses air pushed across the surface of the coffee cup due to the fan providing a known wind speed of 2.96 something meters per second to aid in heat transport. This fan acts as an external source to increase fluid motion over the source, thus increasing heat transfer compared to natural convection. These results agree with the idea portrayed in class literature and comes to a conclusion that coffee is better cooled due to forced convection rather than natural convection.
This graph here shows our experimental versus actual data for natural convection. As you can see, there's a little bit of error here, and that's because we made some assumptions when doing the experiment. Since we couldn't measure the surface temperature of the cup due to not having the equipment to do so, we assumed the surface temperature would be equal to the liquid temperature in order to do our calculations. This obviously was not the case because the cup provides some kind of thermal resistance.
For our calculated results versus our experimental results for forced convection, we can see they were a lot closer to what was actually happening in the experiment. However, we assumed for our calculations that it would be a constant heat transfer throughout the forced convection, which leads to the discrepancy in here due to the buildup of the thermal boundary layer. There is a temperature difference in the calculation with time as it progresses.
In summary, we can conclude that forced convection is much more effective than natural convection in cooling coffee. Throughout our experiment and calculations, we made several assumptions, including that coffee has the same properties as water, that there was a constant rate of heat loss, the surface temperature was equal to the overall temperature, and there was no heat loss due to resistance in the cup. These assumptions are what attributed to our errors in the experiment and calculated temperatures. We were also not in an isolated environment, which could have resulted in different modes of heat transfer that we did not calculate for.